Hey math fans, Alex here, and in the last video we talked about and introduced the binomial distribution, which recall if x is a binomial random variable with parameters n and p, I should specify that n is going to be the number of Bernoulli trials, where Bernoulli trials have the same probability of occurring and are independently and identically distributed, and little p is going to be the probability of a success. Okay, so each trial only has two possible outcomes, either a success or a failure, like flipping a coin. Okay, and we had these three properties. So the first one is that the probability that your random variable takes on this many successes is going to be n choose x times the probability raised to the x power times q to the n minus x power, which remember that q was just 1 minus p. Or the probability of a failure. Okay, the expected value of the binomial distribution was just n times p, and the variance was n times p times q. So we proved all of that last time, and let's dive right into an example. Okay, so this is going to be the random walk problem in one dimension, and it says, let a person who might be under the influence of alcohol take capital N steps along a number line, where taking a step to the right occurs with probability p. Okay, so that's going to be our event that's a success. And we want to know the probability of making it home if his house is 50 units away. Okay, so the first thing that we should probably do is define capital N as number of steps taken to the left plus the number of steps taken to the right. Okay, and I'm going to go ahead and say also that capital N is going to be the sum of n1 and n2, where n1 is the number of steps to the left and n2 is the number of steps to the right. Okay, so what does it mean to make it home? Well, that means that the number of steps taken to the right has to surpass the number of steps taken to the left by a factor of 50. We'll say exactly 50 for now. Okay, so what that means is that n2 minus n1 needs to equal 50. Okay, but we know that n1 can be solved for, and we know that n1 is actually equal to big N minus n2. Okay, and that's going to equal 50. Okay, so then solving for n2, we get that n2 should equal capital N plus 50 all divided by 2. Okay, so n2 is going to be your random variable. Okay, it's going to be a binomial variable because it's the number of successes in capital N Bernoulli trials, where each trial is either to the right or it's not to the right. So that is our event that is either a success or not a success. Okay, so let's go ahead and define that a little bit more formally. Okay, so let maybe capital X be number of steps taken to the right. Okay. Clearly, this is a binomial distribution. Okay, with capital N Bernoulli trials and probability of success p, and recall that is all we need to specify the binomial distribution for each trial. Okay, so suppose, for instance, capital N is equal to 1500. So he's taking 1500 steps, which if you think about it is less than a mile. Okay, each step is a couple of feet, but maybe he's really drunk and intoxicated and every single step is an exertion. Plus he's turning around a lot, so he's getting a lot of exercise. And the probability of success will make it 50%. So him choosing to go right is the same as choosing to go left because he's impaired and has no idea where he's going. Okay, so then we know that N2 is then going to be this capital N plus 50 over 2, which is 1500 plus 50 divided by 2, which is 775. So that's the number of successes that we want. So we have that the probability that x is equal to, say, N2, well, remember, that's just going to be capital N choose N2 times the probability of success to the N2 times the probability of failure to the capital N minus N2. But plugging in the numbers, we get probability that x is actually 775 is going to be 1500 choose 775 times 0.5 to the 775 times 0.5 to the 1500 minus 775. Okay, and I'm going to type that into my calculator really quickly. And I got 0.00896. Okay, so pretty unlikely. Let's kind of amend this probability slightly and go back to the original scenario, because I don't think we want to know exactly when the number of steps to the right surpasses the number of steps to the left by exactly 50. We want it to surpass it by at least 50, right? Because we're assuming that, when he gets home, maybe the individual has a significant other who takes him in and takes care of him, or the drunk person just kind of knows that when he's home, he can just stop. Okay. So what we really want is the probability that x is bigger than or equal to 775. Okay. And the question is, how are we going to find that? Well, first thing that we want to do is we want to note that that is going to be equal to 1 minus the probability that x is less than and not equal to 775. Okay? And then what we have is we have a situation in which we have kind of a cumulative distribution function. And if we knew what the CDF was for the binomial distribution, we could just plug it in. But unfortunately, we don't. And although you can derive it, it's kind of beyond the point that I'm trying to make. So at this level, we don't really need to even rewrite it like this. We're just going to use a calculator. Okay, there are online calculators that do this kind of thing for you. I'm going to show you the one that I most commonly use, and I'm going to set a link in the description. So I'll be right back where I show you all the binomial calculator. Okay, so this is stattrek.com, and just hit binomial. And so the probability of success is 0.5. The number of trials was 1,500, and we wanted 775 successes. And when you calculate, it gives you all these fun things. So it gives you the probability that it's exactly 775, and that's how I got 0.00896. If you wanted this cumulative probability, it gives you that. We want specifically that it is greater than or equal to 775, so we get an answer of 0.1029. So we can go ahead and note that, 0.1029, okay, which is our answer. Okay, which is a lot more likely. So with odds about 10% that he makes it home. Now, what factors influence this? Well, clearly, if the number of steps is larger, that means that there's more variability, which means there's more chance that he deviates towards his house. Okay, now if the house was further away, that would obviously make it more difficult. Okay, so that's that. Now, the next thing that I want to do is I want to discuss if there's a way that we could possibly approximate the binomial distribution. Okay, so can we approximate a binomial distribution with parameters? I'll just go back to little n and little p. In other words, is there a way that I can, for k successes, or for little x successes, can we approximate that probability that x is equal to little x is equal to n choose x, p to the x, 1 minus p to the n minus x. That's ultimately what we're trying to approximate. And the reason that we want to approximate that is, recall that this binomial coefficient is equal to an expression that involves factorials. Okay, so that is equal to n factorial divided by x factorial n minus x factorial, which is computationally problematic. Now, the calculator that I had was able to do 1,500 trials, and while that sounds like a lot, sometimes you want tens of thousands, if not millions of trials. Okay, so to do that, it would be very, very useful to have some sort of approximation on the back burner, so that's what we're going to spend some time to do. Okay, let's go ahead and do that. So the first thing that I'm going to do is I'm going to note that we're going to first find the probability that the number of successes is equal to 0. Okay, the idea is if you want the probability that the number of successes is little x, you actually we're going to come up with a formula that is a recursive formula that's based on the previous term, x minus 1, and that's based on x minus 2, and eventually it's going to be based on 0. Okay, so that x equals 0 is going to be really important for us, and then we're going to come up with a general formula. Okay, so what would this be? Well, by definition, this would just be n choose 0 times p to the 0, 1 minus p to the n minus 0. Okay, but this binomial coefficient would just be 1. P to the 0 is 1. And then we get that this is going to be just 1 minus p to the n power. Okay, so how are we going to approximate that? Well, we're going to go ahead and make a small substitution. Okay, so we're going to let the expected value of x, and we're going to define that as m. So for the binomial distribution, remember the expected value is just np, and that implies that p can be substituted with m divided by n. Okay, so why did I do that? Well, we're going to substitute in this value of p for this value of p right here. So we get that the probability that x is equal to 0 should just be 1 minus m over n raised to the n power. Okay, and this is going to be our first approximation. So this is going to be approximately equal to e to the minus m, and I need to specify exactly when we're allowed to make this approximation. If you recall the formula for compound interest, this is actually continuously compounded interest, provided the number of times that you compound goes to infinity, right? So this is the same idea. So this is for large n. That's when we can make this approximation. So keep that in the back of your head. This only works for really, really large n. And we have kind of the first piece of the puzzle. I'll just go ahead and box that. We'll keep that in the back of our mind. Now, in order to find the probability in general that we have little x successes, so to find the probability that x is equal to little x, we're actually going to note this quantity instead. Remember, I said that we wanted a recursive relationship, so that kind of clues you into taking little x and little x minus 1 as successes. And by the way, just to make the notation a little cleaner, I'm just going to go ahead and symbolize this with a function that we're plugging in little x. This is going to be a function where we're plugging in little x minus 1. So keep that in mind. Okay, so then what is this going to equal? Well, this is going to equal n choose x, p to the x, 1 minus p to the n minus x. But on bottom, we just replace x with x minus 1, and we get n choose x minus 1, p to the x minus 1, 1 minus p to the n minus x minus 1. Okay. And then this is going to equal, well, those binomial coefficients, right? So we're going to have that this is, by definition, n factorial divided by x factorial n minus x factorial times the rest of this. That's the numerator. And the denominator is going to be n factorial divided by x minus 1 factorial times n minus x minus 1 factorial times p to the x minus 1 times 1 minus p to the n minus x minus 1. Okay. So, some great stuff happens, a lot of cancellations, and, the first thing that you might notice that automatically cancels the n factorials, which is actually the most important thing that cancels, right? Because if n is obscenely large, which it has to be to make these approximations, like 1,000 factorial doesn't really work. So remember in chapter 1, I mentioned that even a simple graphing calculator can't even do 70 factorial. Okay, so when all is said and done, you're going to get that this is going to be equal to little n minus x plus 1 all over x times p times 1 minus p. Okay, so I'll have you kind of simplify that as an exercise. Okay. But now we have something kind of interesting. So the last thing that I'm going to do is we're going to rewrite this as n minus x plus 1 times this quantity, which I'm going to go ahead and multiply out. So it's going to be p minus p squared all over x. Okay. Now, here's where our next approximation is going to come in. So the first term that I'm going to write down is that this term right here can be approximately the same thing as n, provided what? Well, provided that n is very big compared to x. Okay, so for example, if you're flipping 10,000 coins and you want the probability of getting, say, I don't know, 150 heads. Well, 150 is nothing compared to 10,000, basically. I mean, it's roughly much less than, say, 5%. So you can kind of make that approximation there. And the second thing that we can do is we can simplify this term, the second one. We can simplify that to p, provided what? Well, provided that p is very small. Okay, because then if you square p and it's really small, that's approximately just p. Take something like 0.05 and square it, and that's essentially so close to 0 that you can just ignore it. And again, this is all for large n and small p. So for that, we're then going to divide that by x. Okay. Okay, so let me just kind of summarize. So conclusion so far. So the conclusion is that the probability of x divided by the probability of getting x minus 1 successes is approximately np divided by x. Okay, so then this is going to imply, this implies that the probability of success can be defined recursively as being np over x times the probability of getting x minus 1 successes. So then it stands to reason that we can kind of continue this process inductively. And I'm only going to really do this for one more just so you see the pattern. So px sub x is going to approximately be np divided by x times probability of getting x minus 1 successes. But then that's going to be what? Well, this term right here, we can plug that in. Okay, so that's going to be np over x times what? Well, that's going to be np over not x, but this argument right here. So it's going to be np divided by x minus 1 times probability of now getting x minus 2 successes. Okay. And thus, we have that the probability getting x successes, if we continue this process, what we're eventually going to get is we're going to get np to the x divided by x factorial times the probability of getting 0 successes. Okay, so that's going to be another exercise where you just quickly verify that. Okay. But remember, we've seen a probability of getting 0 successes before. Okay, if I can just scroll up. Remember, that was e to the minus m, where m was just the expected value, which is np. So I'm going to substitute that back in. Okay, so this is going to be equal to, or approximately equal to, np to the x over x factorial times e to the minus np. Okay, so finally, we're going to make one final substitution just to make things easier, because we have this factor of NP everywhere. And really, whenever we've made all these approximations, this isn't the binomial distribution anymore, right? Nothing is equal to what I just wrote down, okay? Because we assumed that for n large and for p small enough, we can make all these approximations. So this is no longer the expected value of the binomial distribution, but we're going to go ahead and let lambda equal this NP. So we get that the probability of x equaling little x, we can say that that is equal to lambda to the x over x factorial times e to the minus x. Okay? And so as long as lambda, sorry, this is a lambda. Maybe x was a poor variable choice, but sorry. Okay, so as long as lambda is positive, and as long as x is not negative, then any random variable x whose PDF is star, which we can go ahead and call this star, is said to be, this is going to be our second of the important distributions, but is said to be Poisson. Okay? And remember, just like the binomial distribution, had two parameters, little n and p, but all the Poisson distribution has is lambda. That's it. Everything is in terms of this lambda. Lambda doesn't need to be the n times p from the binomial approximation, or the binomial distribution, although it probably is. But everything's going to be in terms of this lambda, as we'll see in the next video. Okay? So I think that's all I wanted to do right now. Hopefully we kind of did an example using the random walk problem to illustrate the binomial distribution. Then we learned that when we approximate that, we get a brand new distribution called the Poisson. The next video, we're going to discover some properties of Poisson as well as do some examples. So hope to see you there and have a great rest of your day.